Imagine slipping straight through enemy airspace without being seen on radar. Step inside the stealthy B-2 Spirit bomber, a billion-dollar flying wing packed with a devastating arsenal. The B-2 Spirit does not look like any other military aircraft in the sky. Without a traditional tail or distinct fuselage, the entire airframe functions as one massive, blended wing. This unique shape distributes the heavy payload evenly across the entire surface while cutting through the air with minimal drag. Northrop Grumman engineers designed this layout to maximize both fuel efficiency and weapon capacity. A single B-2 can carry up to 40,000 pounds of precision-guided munitions or nuclear payloads. During a real combat mission, the crew flies deep into hostile territory, relying on a complex mix of satellite and terrain-following sensors to navigate without giving away their position. The large, sweeping wingspan stretches over 170 feet, housing 4 massive General Electric engines deep inside the structure. Maintaining it requires a specialized, climate-controlled hangar just to protect the delicate skin from heat and moisture. Every detail is built for long-range, high-altitude strikes. The unique shape is only the first layer of defense, as the outer angles play a massive role in dodging radar waves. Standard military jets feature sharp vertical tails and flat surfaces that reflect radar energy straight back to enemy antennas. The B-2 eliminates these dead giveaways by removing the vertical tail fins entirely. The entire leading edge of the wing sweeps back at a precise 33-degree angle. This specific geometry scatters incoming radar signals in different directions, ensuring almost nothing bounces back to the source. When an enemy radar station sweeps the horizon, the bomber appears no larger than a small bird on the screen. The engine intakes sit on top of the upper surface of the wing rather than hanging underneath, hiding the spinning fan blades from ground-based sensors. Engineers also integrated the exhaust ports into the upper wing surface to cool the hot exhaust gases before they leave the aircraft. This layout means the plane can operate in the contested airspace of the Pacific or Eastern Europe while remaining completely invisible to local tracking systems. This outer shell also relies on a complex mix of specialized materials to absorb incoming radar waves. The physical shape of the wing is only half of the stealth equation. The exterior of the B-2 is coated in advanced, highly sensitive radar-absorbent materials designed to trap incoming radio waves. These composite skins contain complex chemical compounds that convert radar energy into tiny amounts of heat. The maintenance crew works constantly to inspect and repair this fragile coating. If a single panel gets scratched or exposed to extreme heat, it can ruin the stealth profile of the entire jet. In fact, an incident during a routine 2010 ground operation showed just how sensitive this layer is when a fuel leak caused a fire that damaged the specialized skin, grounding the aircraft for months of complex repairs. The outer layers must withstand extreme friction and freezing temperatures at high altitudes without losing their effectiveness. This level of engineering makes it incredibly challenging for the maintenance crew to keep the plane mission-ready. Hiding the shape of an aircraft is not enough if enemy sensors can spot the massive heat signature coming from the exhaust. The B-2 Spirit hides its 4 General Electric F118 GE100 engines deep within the wing structure to keep them away from prying eyes. Air travels through S-shaped intake ducts, which block radar waves from bouncing off the spinning compressor blades. Once the air passes through the engine, the exhaust flows over a set of heat-resistant, titanium-coated panels. This layer cools the hot gas before it exits the aircraft, making it nearly invisible to infrared tracking systems. This design protects the plane against modern heat-seeking surface-to-air missiles. If an engine catches fire or suffers a technical fault, the onboard fire suppression systems isolate the damage immediately. Engineers at Northrop Grumman spent years refining the exhaust cooling process. In fact, early testing showed that even minor exhaust leaks could melt the surrounding composite materials, which forced the team to use advanced titanium and ceramic heat shields. Managing 4 separate engines while keeping the weight balanced takes immense computing power. The pilots rely on a digital brain that makes constant adjustments during the flight to keep the aircraft steady and safe. These adjustments are completely managed by advanced fly-by-wire flight control computers. The flying wing design lacks a traditional tail, making it inherently unstable in the air. Without a computer actively calculating control inputs, the aircraft would tumble out of control within seconds. The flight control system uses 4 redundant computers to process input from various sensors and adjust the control surfaces thousands of times per second. This digital brain calculates the perfect angle for the wing panels, maintaining complete stability in rough weather. When the bomber flies at high altitudes, these computers adjust the trim and throttle to ensure maximum fuel efficiency and range. If a failure occurs in one channel, the remaining systems take over instantly. This level of automation allows the 2-person crew to focus entirely on navigating and managing the weapons bay during long missions. The technology inside this system represents decades of aerospace development. It is the exact reason the bomber can fly at 50,000 feet without dropping off the radar. The computing architecture must endure severe vibrations and freezing temperatures without failing. This level of control ensures the plane can carry a massive payload deep into enemy territory. Flying high above the reach of conventional anti-aircraft artillery gives the B-2 Spirit a massive tactical advantage. The 2 internal bomb bays can carry up to 40,000 pounds of weapons, including satellite-guided bombs and heavy bunker busters. The weight must be distributed perfectly to prevent the heavy payload from shifting the center of gravity. Hydraulic rotary launchers inside the bays hold the munitions in place until the moment of release. During combat operations, the crew opens the doors for just a few seconds to minimize the radar signature during the attack run. Some of its most famous sorties include the 30-hour non-stop combat mission from Whiteman Air Force Base to targets in Afghanistan in 2001, pulling off some of the longest and most difficult strike packages in modern military history. In one historical incident over Kosovo, the bomber dropped multiple joint direct attack munitions in a single pass, completely destroying fortified targets while staying far above the reach of surface threats. The onboard system calculates the exact trajectory before dropping the payload, ensuring precision hits even from high altitudes. Every door and internal rail is designed to operate in freezing, low-pressure conditions without freezing shut. This immense capability places a heavy burden on the ground teams, who must reload and inspect the intricate systems between flights. The turnaround process requires a highly skilled crew working around the clock to prep the aircraft for its next long-range mission. Preparing this delicate, high-tech machine for combat takes a massive amount of time and precision on the ground. Keeping the fleet operational remains a challenge due to the fragile nature of the materials and the complexity of the onboard computers. Every flight requires hours of post-flight inspection to ensure no structural damage or radar-absorbing material degradation has occurred. Specialized facilities are required to maintain the skin, as standard hangars cannot accommodate the large wingspan. The maintenance personnel work with extreme caution, using temperature-controlled environments to cure the protective coatings correctly. If a component fails, the technicians must access the systems through tight panels without damaging the surrounding composite structure. The high cost of maintaining the fleet means that only a small portion of the bombers is active at any given moment. Air Force officials constantly look for ways to upgrade the avionics and engines to extend the service life of the airframe. Despite the intense maintenance demands, the B-2 remains an important part of the long-range strike fleet, providing a reliable deterrent against global threats. The aircraft proves that advanced engineering and careful maintenance can keep a complex machine flying for decades. The development of this machine set a new standard for modern aerospace design.